The second lecture on interpolation. In the last class we were discussing about the forward difference formula, and we have calculated the forward difference of y0 of first order difference, second order difference, third order difference, and generalized this. And then we were about to calculate the differences, these forward differences from the forward difference table. Due to some technical problem, the video capturing was interrupted, so we had to start the rest part in the second video. Now we have a pair of xy values. The I is running from 1 to 3, so we have four values of x available. So as we have 4 values of x available, we can calculate at most delta 3 of y0. The delta 4 of y0 or higher order difference we cannot calculate because it will require the information about y4, y5 and so on and so forth, which are not available. And the corresponding y values are given in this table. Now first is, this is the value of y0, y1, y2, y3. So if we calculate delta of y0, that means this is y1 minus y0, which is 2. Then if we calculate delta of y1, which is y2 minus y1, which is y2 minus y1, so this is del 50. So this is delta of y0, this is delta of y1, and delta of y2 is equal to y3 minus y2. So this is. Now we come to second difference. Second difference of y0 is actually, second difference of y0 is this one, which can be written as delta of y1 minus delta of y0. So this is the second difference there. This is delta 2 of y0, which is delta y1 minus delta of y0. So this is thus. And similarly, delta 2 of y1 is this minus this as 96. The third difference of y0 is 96 minus 48 is 48. And we cannot calculate delta 3 of y1 because that will involve, that is required the information about y4. So this is the forward difference for table. If we move along this diagonal element, we get y0, delta y0, delta 2 y0, delta 3 y0, and so on and so forth. That's why it is known as the diagonal difference table. And as we are moving towards the right, starting from a particular value, which is called forward difference table. If we were to calculate delta y1, etc. So this is y1, this is delta y1, this is delta 2 y1. Y3, this is y3, this is delta of y3. As the number of data are small, so we cannot calculate higher derivatives of higher differences of y's. So this is the use of difference table. And if it is found that this difference comes out to be a constant, then the higher order difference will obviously be 0, wherefrom we can conclude that the order of the polynomial. If delta 4 becomes 0, then we conclude that it is a polynomial of order 4. Now we come to Newton's forward formula. So with this equispaced argument, the one interpolation formula differs from the other only by the choice of interpolating polynomial. Now, in Newton's forward interpolation formula, Newton's forward interpolation formula. This formula is applicable for the estimation of values of x which is near the beginning of the tabulated data. We shall come to these points afterwards. We are provided with a sets of x, y, yi data with I ranging from 0, 1 right up to n. So there are n plus 1 data. So the interpolating polynomial, as there are n plus 1 conditions available, phi n, the interpolating polynomial phi n is a polynomial of order n. Phi n may at best. So in Newton's formula, one assumes phi n of x is equal to a0 plus a1 x minus x0 a2 x minus x0 x minus x1. Then the next term is a3 x minus x0 x minus x1 x minus x2 ai. This is the form of the polynomial assumed for in Newton's formula. Now the task remained is to find out the unknown coefficients, the a0, a1, these coefficients. Before going to this, we like to write it in a compact form. Now we introduce a dummy variable I which ranges from 0 to n, so that these terms are taken care of, and this is ai. Then we use the product formula j is equal to 0 to I minus 1 x minus xj. As capital sigma stands for summation, capital pi stands for product. As you might be aware of the fact that if we write I is equal to 0 to 5, then this is I, we call it 1. So this is 1, 2, 3, 4, right up to 5, that is factorial 5. So we can write factorial of an integral order by using the capital pi notation. So this is the compact way of writing the formula. Now, to determine the constants, we recall the requirement that of interpolation, that at a given value of x which belongs to the given set, y is exactly reproduced. At x is equal to xi, phi n of xi is exactly yi. There should be no difference between the interpolating polynomial and the supplied data for the given set of x values. So if we set x is equal to 0, phi n of x0 is equal to y0. If we put x is equal to x0, we see that all the terms except the first one vanishes, so we get a0 as y0. Now we come to phi n of x1, this is y1. If we put this value over there, it is a0 plus a1 x1 minus x0, x1 minus x0. So this is h, x1 minus x0. As the arguments are equispaced, we get it. For a0 we write y0, and this is a into h, as the spacing is equispaced. So xi is equal to a plus ih, with h is equal to b minus a by n. This readily gives us that a1 is equal to y1 minus y0 by h. If we introduce the difference formula, this is delta y0 by h. The forward difference that we have discussed in the earlier class. Now phi n at x is equal to 2 is equal to y2, and coming to this formula, all terms to the right of this are 0. So the result is a0 plus a1. This is x2 minus x0. For the next term, we have a2 x2 minus x0, x2 minus x1. Now coming to the situation, this is y0. a1, we have calculated a1. This much is twice h, and this is, so this is altogether twice y1 minus y0. Now again let me explain. a1 is y1 minus y0 by h, and this much is twice h, so the h in the denominator gets cancelled, and this is a 2 factor. And for this part we have a2, this is 2h, and this is h, 2h square. So if we write 2h square a2 is equal to y2 minus twice y1 plus y0. This is minus 2y0, this is plus y0, so this is minus y0. When it is taken to the other side, it becomes positive. This is delta 2 of y0, which gives us a2 is equal to delta 2 y0 divided by factorial 2h square. Now I think the use of difference table becomes obvious. If we go on putting the higher values of this, we get the corresponding coefficients. So this is xi is equal to exactly yi, which on explicit evaluation gives you xi is equal to factorial I h to the power I. So we rewrite this term as for AI we write this one This is the Newton's formula. And this formula, now let us consider the value of x at which we are to estimate the function so that let us consider that x, we write x is equal to x0 plus ph. This is the value of x at which we want to find out the polynomial. So value of x, this is our question. Say for example, in the case that we cited, these are the corresponding x0, x1, x2. We are interested about this value of x. The x is equal to 1915. So x is equal to 1915. X0 is 1900, and we are to, and h is 10. So we are to calculate p. Or for x0, we may rewrite this expression in terms of p. So first of all, we consider this term x minus xj. This is equal to x0 plus ph minus x0 minus jh. So x0 cancels out, x0 plus jh. So this is p minus j times h, this term. So with j is equal to 0, this is ph, then p minus 1h, then p minus 2h, h, and so on and so forth. This is p minus j plus 1h. So there are h appears I times, which removes this part. This no, let me correct it so that summation over j is equal to 0 to I minus 1 x minus xj. This is x minus x0, x minus x1 right up to x minus xi minus 1. For x minus x0, this is j, this 0, so this is p into h. For this term, it is p minus 1 into h, and so on, so forth. Ultimately, for this term, p minus I plus 1h. So h tab here, this can be written as p minus 1 right up to p minus I plus 1 h to the power I. This h to the power I cancels with this, and if we consider this I factorial and use the generalized combination notation, pi is equal to p minus 1 right up to p minus I plus 1 by I factorial. So if we consider this, it can be written as this part, and this part all together goes into the generalized combination notation. So this is pi combination of pi and delta I of y0. This is the compact way of writing Newton's forward formula. we can arrive at this formula most easily by another way. We shall first describe the approach, and this formula, particularly this formula, can be obtained in an alternative way, which is very easier. Say our problem is to find out value of the polynomial. Let me first write the formula. Phi n for forward interpolation formula is equal to summation over I is equal to 0 to n ai. Which becomes this one. Which finally becomes where x is written as x0 plus ph. Now our aim is to find out the value of phi y at x, which is y at x0 plus ph, that is the value of y at a plus ph. That means there are pth increment of this. We know delta of y of a is equal to y of a plus h minus y at a. There is another operator, this is the difference operator, that is another operator called increment operator, which simply increases the y value by x value by a. So we can write it as e minus 1 of y at a. This is the increment operator. So the action of the increment operator on y on xi is simply to y of xi plus 1. Just the x value is increased by 1. In that sense, we can, if we use E2 twice on y at xi, it is y of xi plus 2. In that case, we can write it as EP operating on y of a, or y of x0. And there is another formula from here we can develop, that delta operator is equivalent to E minus identity operator, or E operator is equivalent to 1 plus delta operator. So we can write it 1 plus delta operator to the power p operating on y of a. We expand this quantity in binomial series for fractional index. Note that since x, the value of x at which we want to estimate the value of y does not belong to one of the tabulated values, so that p is not an integer, p is a fraction, so it is a binomial expansion of fractional order. So we write it as I is equal to 0 to infinity and delta I of y at a. Now this is the analytical expression, but if we want to calculate delta 4 of y, then if we want to calculate delta 4 of y0, this is y4 minus 4y3 plus 6y2 minus 4y1 plus y0. So calculation of delta 4 requires a knowledge of y4, but we are provided with the values up to yn, so we cannot calculate the differences of higher than n, so we approximate these up to n values. This is nothing but this formula. So this restriction comes from the fact that we are not provided with infinitely large number of y values, so we are provided with a finite number of y values, so we can calculate differences up to a particular order. If we are provided with 11 data, then we can at most calculate 10th order difference. That sets in a limitation in the infinite series expansion. And another thing you might recall that in the difference table, the maximum number of differences were available for y0. And if we start with a value of x which is near the bottom of the table, then this requires the value of x lies between x3 and x4. If it lies between x3 and x4, then the difference table should start with x3, and we will be provided with lesser number of differences, and that is to say the polynomial becomes of lesser and lesser order as the value of x goes down the tabulation, and the error will be increased gradually. So to say, the Newton's forward interpolation formula is correct one when the value of x at which we are to estimate the function lies near the beginning of the table. Let me first let me apply the theory to a given set of data and calculate the difference. For we shall apply this formula to a given set of data that we presented earlier. For the application of Newton's forward formula, I have used a table which is not the one which we have used earlier in discussing the difference formula. The difference table. This is a one new data. The I is there are 5 data available. I am starting from I is equal to 0 to 4. The x values are equispaced starting from 0 to 8, so that x0 is 0 and the h, the spacing between x values, is 2. And these are the corresponding y values. The first difference is 13 minus 1 14, 43 minus 13 30, 89 minus 43 46, 151 minus this is this. Now second difference is this minus this is 16, this minus this is 16, this minus this is 16. So the second difference has become a constant, and the third one differences are 0. Recall the use of Newton's formula is that when we have used this, we see that the third difference onwards are 0. So it is apparent that the data should fit exactly to a polynomial of order 2, that a parabolic fit is sufficient because the expansion involves y0, then y1, then y2, y3 onwards are 0. So the phi n here becomes a0, a1 of x minus x0 plus a2 x minus x0, x minus x1. All other higher a is a 0, so the data should match to a polynomial expansion. And if we are to calculate the value of y at x is equal to 3, so phi n at x is equal to 3 is equal to y0 plus, I am using this formula, p delta y0 plus p into p minus 1 by factorial 2 delta 2 y0. This data enables us to calculate up to delta 4, but since these are 0, we are not including any more terms, and p is equal to 1.5 and y0 is minus 1, y0 is minus 1, this is for y0, p is 3 by 2, delta of y0 is 14 plus 3 by 2 into 1 by 2 into delta 2 of y1 is 16. So this is minus 1 plus 21, and this is 8 plus 6. Sorry. The value is 14. Oh, sorry. 26 plus it is 26 is the value. I tried to feed this data. I feed this data in computer and given a polynomial fit of order 4. It is found that the A0, A0, A1, A2, these are non-zero. Let me quote the exact value that I have used. This is of the order of minus 16, this is of the order of minus 10 to the power 15, so they are 0. And the other values that we have obtained is A2 is 2, A2 is 2, we have obtained A2 is 2, this is equal to Y1 is minus 1, Y0 is minus 1, and this is around 7. These are the values that I have obtained. This is the point that I was talking about at the beginning. Here we see that the data that are supplied matches with a parabolic fit. So the first three coefficients have significant values. The higher coefficients that have been included here are insignificant, because in the expansion these A3, A4 are 0, which has appeared by the very low value in numerical calculation. So to say, if we were provided with only first three data, we could get almost exact result apart from the truncation error for all values of x in this range. That's all about the for Newton's forward formula. In the next class we shall discuss the Lagrange's interpolation formula. Recall that Newton's forward interpolation formula has some restriction. One is it is applicable to equispaced arguments, and it gives good result only when x lies very near to the starting point. If the x point were chosen to be over here, then only one value would be available. So only y of 4, no difference of we cannot calculate the difference of y4 because delta of y4 is defined as y5 minus y4. Since we do not have any knowledge about y5, we cannot calculate even the first difference of y4. So the series, this data can be fitted to a polynomial of order 4, but if we choose the value of x to be here, then it uses up this the polynomial reduces to a polynomial of order 1, that is a constant function there, and consequently a huge error is being incorporated. And in the next class, we shall consider Lagrange's interpolation formula, which is applicable for equispaced as well as in inequispaced intervals. There is no restriction on the x values. X value can be anywhere towards the end, towards the beginning, or at the middle. And furthermore, the Lagrange's formula is very useful for inverse interpolation. That is, knowing the value of y, we can also get the corresponding value of x, as we have to do it very frequently in actual experiments. And another thing, Newton's Lagrange's formula is also suitable for extrapolation. That is, if we want to find out what is the value of the interpolating polynomial at x is equal to 10 or for x greater than 8 or less than 0. The Lagrange's formula can also be used suitably to such situation. In that sense, Lagrange's interpolation formula is more general in nature, but so far the hand calculation is concerned, Newton's formula is very suitable, as we have done it very easily over here. That's why Newton's formulae, I must say formulae because there are other formulas of due to Newton and Gregory too, which were very suitable for hand calculation, and that's why they were very popular at yesteryears. But with the advent of high-speed computers, implementation of Lagrange's interpolation formula is not a problem at all. So it would be better to make us conversant with the Lagrange's formula, which has more general nature than the Newton's one.